Beneath the calm waters separating Denmark and Germany lies a strait that once forced Europe to move slower than its ambitions, until engineers set out to redraw the continent's infrastructure. Their project, initially a bold alternative, evolved through a major breakthrough that upended traditional engineering norms, resulting in a tunnel designed to withstand storms of unprecedented ferocity in the Baltic Sea. So, how was this extraordinary metamorphosis possible? And what challenges shaped every decision along the way? Let's go to the heart of the project to discover the technological epic playing out beneath the waves. The strait that held Europe back. For decades, the Fehmarnbelt served as a quiet but stubborn barrier between Denmark and Germany, shaping the flow of people and goods across northern Europe in ways few travelers ever suspected. This narrow strait interrupted the Scandinavia-Mediterranean corridor, a 4,800 km economic backbone stretching from Finland's ports to Italy's markets, creating a logistical weakness whose repercussions extended far beyond its modest width. Freight convoys moving between continents were forced to choose between slow ferries that devoured precious hours or a long westward detour that strained infrastructure not designed for such constant pressure. Over time, delays piled up, causing tens of billions in yearly losses, slowing growth in regions relying on fast, predictable transport heavily. Yet the strait remained without a fixed link, not because the need was unclear, but because the Baltic Sea concealed a geological challenge capable of thwarting even the most determined proposals. Beneath the waters lay an unpredictable mix of soft clay and hard limestone that made traditional tunneling dangerously unstable, while the harshness of the winter seas discouraged any attempt to build an exposed bridge. As traffic grew and pressure mounted, governments recognized that a transformative solution could no longer be deferred. Why conventional engineering couldn't win? When planners first revisited the idea of connecting Denmark to Germany, they ran into a problem that had silenced previous proposals time and again. The Baltic seabed simply refused to cooperate with conventional engineering. Tunnelers, used to cutting steadily through uniform rock in many of the world's biggest underground passages, faced a treacherous mix here: hard limestone, shifting clay, and unpredictable voids beneath the Fehmarnbelt Strait itself. Any miscalculation could have led to flooding, jammed machinery, or a catastrophic structural failure, turning a megaproject into a multi-billion-dollar hazard. These risks made politicians, engineers, and financiers ask if intuition was responsible. Alternative long-span bridge challenged. Winter storms in the Baltic Sea can produce winds and waves powerful enough to threaten tall pylons, while maritime traffic demands a clearance height that pushes bridge engineering to its limits. Environmental concerns further complicated the picture, as the massive foundations of a bridge could disrupt fragile coastal ecosystems already under pressure. Years of study showed no traditional method fully met safety, cost, environmental, and long-term reliability needs. It was during this period of reassessment that a remarkable shift occurred. Instead of forcing a tunnel through uncooperative soil or erecting a bridge vulnerable to rough seas, engineers proposed building the entire structure on land, where conditions could be controlled, and then immersing each giant section into a trench dredged on the seabed. Unconventional at first, this solution balanced ambition with caution, forging a design philosophy that reshaped the project from foundation to finish. Building a factory the size of a small town. After approval of the immersed tunnel method, the project moved from theory to reality on Denmark's coast, where engineers built an unprecedented European fabrication complex. At Erdbehaven, this 500,000 m2 plant, built solely for tunnel parts, ran like an industrial ecosystem, with zones for steel shaping, concrete casting, curing, assembly, storage, and QA. Its area rivaled that of a small town, and its purpose was singular: to produce colossal structures with millimeter precision in an environment shielded from the unpredictable conditions of the open sea. Inside the plant, the process began with reinforced steel rebar cages, giving work tensile strength concrete lacks. Workers cut, bent, and assembled immense steel bars into imposing trusses, each shaped to meet the exact technical specifications required for structural integrity under constant sea pressure. Once completed, these cages were positioned inside vast formwork systems where concrete was poured, vibrated, leveled, and then left to cure for several weeks to achieve the durability needed for centuries of service. Each step controlled temperature, humidity, and material texture, ensuring fully consistent performance across every component. After curing, 24-meter segments each were joined into 217-meter tunnel elements, weighing nearly 73,000 tons overall together, lined up in open-air storage basins. These finished elements resembled horizontal skyscrapers awaiting their deployment. The factory could house nearly 90 of these giants, creating an inventory that allowed offshore operations to proceed without interruption whenever a weather window opened. This orchestration of precision land-based manufacturing for structures destined for the ocean became one of the project's most innovative achievements, bridging the gap between controlled industrial engineering and the unpredictable demands of the sea. Sink skyscrapers beneath sea. After each tunnel section is finished, the job moves from land control to careful maneuvers, setting huge units down on seabed precisely. Engineers approach this task with the precision of aerospace operations, as the slightest deviation during installation could compromise the entire 18 km corridor. Each section, sealed by watertight bulkheads at both ends, acts like a floating concrete hull. Ballasts along its length let crews tune draft, so the structure can be steered from harbor to sea in balance. Tugboats guide these giants through the Fehmarnbelt, but not alone. Immersion pontoons, floating platforms with heavy-duty winches, lock on, giving precise control as the unit drifts above the dredged trench. Sensors, GPS, and hydraulic monitors work together to check orientation, keeping it aligned despite currents and winds. Each move is slow, often hours long, while operators carefully watch ballast balance and the subtle buoyancy-gravity tug-of-war. Once alignment meets tolerance, engineers begin immersion, then carefully fill the ballast tanks. The unit lowers under control, guided by winches, continuously watched by underwater survey gear. Once it hits the seabed, extra tweaks align it within just a few millimeters. Next, it must be joined to the previous section by using pressure differences pump water from the sealed chamber between them. Outside seawater then drives the parts together under immense pressure, with inner seals and reinforced concrete securing the joint. The structure turns watertight, ready for the next segment, pushing the tunnel forward, designing for a storm the world has never known. As the tunnel advanced segment by segment under the Fehmarnbelt, engineers met a challenge beyond underwater assembly mechanics. Climate research during the design phase revealed a troubling trend. The Baltic Sea, once considered relatively predictable, is expected to see stronger storm surges, higher sea levels, and more unpredictable waves over the next century. These results made the team rethink durability assumptions. A structure meant to serve Europe for generations couldn't rely on today's conditions alone. Instead, it needed the resilience to withstand a type of extreme weather event so rare that it appears only in long-term geological probability models. This requirement led to one of the most extraordinary engineering decisions in the entire project. The Fehmarnbelt fixed link would be designed to withstand a storm with a 2,000-year return period, a benchmark far more demanding than the standards applied to conventional immersed tunnels. To achieve this, it was necessary to thicken critical wall sections, reshape the exterior surfaces to reduce hydrodynamic drag, and integrate a redundant sealing system capable of ensuring watertightness even if the primary seal fails. Engineers also modeled how future storm patterns could shift loads along the tunnel's entire length, ensuring the structure can distribute pressures without suffering fatigue or deformation over time. These measures turned the tunnel from transport link into a long-term climate resilience test, reflecting the recognition that major infrastructure built today must anticipate a harsher ocean environment tomorrow. This philosophy let projects set worldwide precedent. Underwater construction must not only solve today's logistical challenges, but also prepare for environmental forces that future generations may struggle to predict. Fehmarnbelt Tunnel's hidden strength isn't just its materials, it's built to face a changing world for what's next. A link that reshapes a continent. Once the tunnel opens, its effect goes far beyond cutting coast-to-coast travel time. The Fehmarnbelt fixed link entirely reshapes Europe's routes. Travel times between Scandinavia and Central Europe will shrink dramatically, allowing freight trains to cross the strait in just minutes and eliminating the systematic delays tied to ferry schedules. Logistics companies that once had to contend with unpredictable wait times will operate with a level of precision that reshapes their routing strategies, while manufacturers dependent on just-in-time delivery will benefit from a corridor that finally functions as a continuous network rather than a fragmented chain. Tourism and regional mobility will also evolve, as travelers who once avoided this laborious crossing rediscover routes that suddenly become direct and efficient. The economies of Denmark, Germany, Sweden, and beyond will see ripple effects as ports rebalance their roles, highways adapt to new flows, and rail operators integrate this shortcut into their long-distance schedules. The tunnel's presence even fosters cultural and institutional cooperation, because infrastructure that shortens distances often strengthens partnerships that once seemed limited by geography. The Fehmarnbelt fixed link is more than engineering. It's a continental connector reshaping Europe's internal geography. Fehmarnbelt Tunnel proves strict engineering can beat obstacles that once stalled Europe, turning bold plans into durable infrastructure today. If this story has expanded your perspective, please like the video, share it, and subscribe for more documentaries on the forces shaping our world.